We are watching something extraordinary unfold in our solar system right now, and the more data that comes in, the more questions pile up instead of answers. On July 1st of this year, the Atlas telescope in Chile detected what appeared to be another routine celestial visitor. But within days, astronomers confirmed something far more significant. This was 3I Atlas, only the third confirmed interstellar object ever observed passing through our cosmic neighborhood. That designation alone would make headlines. But what we are learning about this comet in real time is forcing scientists to reconsider fundamental assumptions about what interstellar visitors should look like, how they should behave, and whether our instruments are even showing us the full picture. If you want to follow this developing story as new observations come in over the coming weeks and months, make sure you subscribe to this channel, because what happens next with this object could rewrite our understanding of not just comets, but the very origins of matter in our galaxy. Let's establish what we know for certain. 3I Atlas completed its closest approach to the Sun, known as perihelion, on October 29th at a distance of 1.36 astronomical units, which places it slightly beyond Earth's orbit from our star. It survived that encounter without breaking apart, a detail that might seem mundane but is actually critical given what happened to previous interstellar visitor 2I Borisov, which showed signs of fragmentation. Right now, 3I Atlas is racing away from the inner solar system, and on December 19th, it will make its closest pass to Earth at a distance of approximately 270 million kilometers. That is comfortably distant, well beyond any possibility of impact, but close enough that our best telescopes, both ground-based and orbital, have an unprecedented opportunity to study an object that does not belong to our Sun's family of worlds. This is where the intrigue begins, because the data streaming in from multiple space agencies is painting a picture that does not fit neatly into our existing models of what interstellar comets are supposed to be. On November 19th, NASA released a collection of images captured by an impressive array of spacecraft: Stereo, SOHO, the Mars Reconnaissance Orbiter, MAVEN, Psyche, and Lucy. These are not amateur instruments. These are billion-dollar missions equipped with cutting-edge sensors designed specifically to observe solar activity, planetary atmospheres, and deep space phenomena. What they captured was a comet displaying a tail stretching up to 5 million kilometers into space, a gossamer stream of material blown back by solar radiation pressure. But here is the crucial detail. Alongside that conventional tail, there is an antitail, a forward-pointing structure aimed directly at the Sun, extending roughly 1 million kilometers. Antitails are not unknown in cometary science. They occur when larger, heavier dust particles lag behind in the comet's orbit, creating an optical illusion from our vantage point on Earth that makes it appear as though material is streaming toward the Sun, rather than away from it. Comet McNaught in 2007 displayed a spectacular antitail. But what makes 3I Atlas unusual is the timescale and velocity involved. This antitail formed over nearly a month, and spectroscopic analysis indicates the particles are moving at just 400 meters per second. For context, that is remarkably slow compared to typical cometary outgassing velocities, which often exceed 1 kilometer per second. Why is material being ejected so gently from this object? What mechanism could produce such a sustained, low-velocity stream of particles over such an extended period? Let's look closer at the data on composition, because this is where 3I Atlas begins to separate itself not just from solar system comets, but from the two previous interstellar visitors as well. Spectroscopic observations reveal an atmosphere dominated by carbon dioxide with remarkably low water content. The ratio of carbon dioxide to water is approximately 8:1. To put that in perspective, most comets we have studied in detail, including those from the Oort cloud at the edge of our solar system, show the opposite trend. Water ice is typically the dominant volatile, with carbon dioxide, carbon monoxide, and methane present in smaller quantities. A carbon dioxide-dominated comet suggests formation in an extremely cold environment, potentially in the outer regions of a protoplanetary disk around a star very different from our Sun, or perhaps in the frigid expanse of interstellar space itself. But even that does not fully explain what we are seeing, because there is another compositional anomaly that has captured the attention of astronomers worldwide: nickel. Spectral lines indicate that 3I Atlas contains nickel at levels 11 to 12 times higher than what we measure in our Sun's photosphere. Nickel is a heavy element, forged in the cores of massive stars and dispersed into space through supernova explosions. The solar abundance of nickel represents the average composition of the material that formed our solar system 4.6 billion years ago. If 3I Atlas has significantly elevated nickel levels, that suggests it formed from material enriched by earlier generations of stellar nucleosynthesis. Based on models of galactic chemical evolution, astronomers estimate this composition points to an age of 7 to 14 billion years. Think about what that means for a moment. This object predates our entire solar system. It is a relic from the early Milky Way, a frozen archive of conditions that existed when our galaxy was young and still forming the heavy elements that would eventually become planets and people. It is, in the words of several researchers, a window into the primordial galaxy. But here is where we hit our first major contradiction, one that has sparked intense debate not just in academic circles, but across social media platforms where amateur astronomers and space enthusiasts scrutinize every released image. The NASA images, despite being captured by more than half a dozen spacecraft with sophisticated sensors, appear surprisingly low in resolution and detail. On November 22nd, an amateur astronomer named Mitsunori Tsumura in Japan released a photograph taken with a half-meter telescope that shows the tail structure of 3I Atlas in exquisite detail, far surpassing the clarity of the official agency releases. Users on X, formerly Twitter, have been dissecting this discrepancy for days now. Why would images from multi-million-dollar space instruments look inferior to a ground-based amateur observation? Several possibilities have been proposed. Perhaps NASA released compressed or downscaled versions for public consumption and is withholding the full resolution data for peer review and analysis. That would be standard practice in some cases, but it fuels suspicion. Perhaps the spacecraft were not optimally positioned, or their instruments were not primarily designed for high-resolution imaging of distant comets, whereas Tsumura's telescope was specifically configured for that exact purpose, with ideal timing and atmospheric conditions. Or, as some more speculative voices suggest, perhaps there is something in the high-resolution data that requires careful interpretation before public release. This is where we must be extremely cautious, because without access to the raw data and the technical specifications of each observation, we are left guessing. But the discrepancy is real, and it has become a focal point for those questioning whether we are getting the complete picture. Now let's turn to the spectroscopic observations from Hubble Space Telescope and the James Webb Space Telescope, because this is where the story takes another unexpected turn. Preliminary data, with full results expected to be released in December, confirmed that 3I Atlas has maintained a remarkably stable brightness, hovering between magnitude 9.8 and 10.2. For those unfamiliar with astronomical magnitudes, that is dim enough to require a decent amateur telescope, but bright enough that serious observers can track it night after night. Photometric analysis also reveals a rotation period of approximately 16 hours, meaning the nucleus completes one full spin roughly every 2/3 of an Earth day. That rotation rate is not unusual for a comet. What is unusual, and this is where eyebrows start to rise in the planetary science community, is the behavior of the gas jets emanating from the surface. Comets produce jets, when sunlight heats volatile ices beneath the surface, causing them to sublimate and burst through weak points in the crust, carrying dust and debris with them. Normally, because the nucleus is irregularly shaped and rotating, these jets appear smeared or asymmetrical when observed over time. They wobble, they shift, they vary in intensity as different regions of the surface rotate in and out of sunlight. But the jets from 3I Atlas appear unusually symmetrical and stable. The gas streams do not show the expected smearing effect. They look almost too clean, too consistent, as if something is regulating their output. This contradicts what we previously thought about how natural cometary outgassing works. Could there be a plausible natural explanation? Absolutely. Perhaps the nucleus has an unusually regular shape, or perhaps the active regions are positioned in such a way that the rotation does not produce the typical smearing we see in other comets. Perhaps the low outgassing velocity we mentioned earlier, just 400 meters per second, contributes to a different visual appearance than we are accustomed to. But it is details like this that have attracted the attention of researchers who specialize in looking for anomalies, and no one has been more vocal about the strangeness of 3I Atlas than Harvard astronomer Avi Loeb. Loeb, who gained widespread attention for his controversial hypothesis that the first interstellar object, 1I de Oumuamua, might have been an artificial probe, published an analysis on November 24th outlining 6 specific anomalies associated with 3I Atlas. Let's walk through them, because even if you disagree with Loeb's more speculative conclusions, the observations he highlights are based on solid data. First, non-gravitational acceleration. When you calculate the trajectory of a comet using only gravitational forces from the Sun and planets, you get a baseline orbital path. But comets do not follow that path exactly, because the jets we just discussed act like tiny rocket engines, pushing the nucleus in directions that depend on where and when the outgassing occurs. Astronomers quantify this using parameters called A1 and A2, which describe the magnitude and direction of these non-gravitational forces. For 3I Atlas, both A1 and A2 are non-zero, which is expected for an active comet. But Loeb points out that the specific values, when combined with the observed mass loss rate, do not fully reconcile. Over the months of October and November, the comet appears to have lost roughly 10% of its estimated minimum mass through outgassing. That is substantial, but according to Loeb's calculations, it does not entirely account for all the observed deviations in trajectory. So what does this actually mean? It could mean our estimates of the comet's mass are incorrect. It could mean there are additional outgassing sources we are not detecting. Or it could mean, as Loeb suggests as a possibility, that there is another mechanism at play. Second anomaly, the shape. In several images, particularly those captured when the comet was closer to the Sun and more active, 3I Atlas appears elongated, stretched in the direction of its motion. This could simply be motion blur in long exposure images, a perfectly mundane photographic artifact. But it also recalls the extreme elongation observed in Oumuamua, which had an estimated axis ratio of at least 6:1, far more extreme than any known natural asteroid or comet. Is 3I Atlas similarly elongated? We do not have resolved images of the nucleus itself, only the coma, the cloud of gas and dust surrounding it, so we cannot say for certain. But the visual similarity has not gone unnoticed. Third, the trajectory. This is where things get particularly interesting from a celestial mechanics standpoint. After 3I Atlas leaves the inner solar system, its path will take it past Jupiter on March 16, 2026, at a distance of 53.4 million kilometers. That might sound like a safe distance, and in terms of collision risk, it absolutely is. But in gravitational terms, that is well within Jupiter's sphere of influence, the region where the giant planet's gravity dominates over the Sun's. Loeb raises a provocative question. If 3I Atlas were not a natural object, but rather a carrier vehicle of some kind, Passing through Jupiter's gravitational field would be an ideal moment to deploy smaller probes. The energy cost would be minimal, and the gravitational slingshot could send those probes toward the inner solar system, including Earth, without requiring onboard propulsion. Is there any evidence that this is happening? No. Is it physically possible? Yes. Should we entertain the idea? That depends on how you balance skepticism with open-mindedness, and this is where the scientific community is deeply divided. Loeb himself acknowledges that the probability of an artificial origin is low. He compares the behavior of 3I Atlas to well-studied natural comets and notes differences, but he stops short of claiming those differences are definitive proof of anything other than the fact that interstellar objects can surprise us. What he is advocating for, and this is an important distinction, is rigorous observation and data collection without preconceived conclusions. The problem is that in the public sphere, particularly on social media, that nuance gets lost and speculation runs wild. On X and other platforms, users are circulating theories that range from plausible to fantastical. Some point to what they describe as a jet structure, rather than a conventional tail, interpreting the narrow, collimated appearance of the gas streams as evidence of directed propulsion. Others claim to have detected radio signals, possibly hydroxyl maser emission, which is a natural phenomenon where molecules in cometary comas amplify microwave radiation, but which in this context gets reinterpreted as potential communication or artificial activity. One of the more elaborate theories suggests that 3I Atlas is actively deploying smaller objects, perhaps probes, designed to monitor Earth, and that it is working in coordination with another comet, C2024 R2 Swan, which also displayed an unusual antitail structure earlier this year. The claim is that these two objects are somehow positioning themselves to surround or observe our planet. This is, to be absolutely clear, unsupported speculation. There is no credible evidence of coordinated activity between two unrelated comets, nor is there any mechanism by which a natural comet could deploy autonomous probes. But the fact that these ideas are circulating and gaining traction speaks to a broader issue. The public is hungry for answers, and in the absence of clear, comprehensive communication from space agencies, people fill the void with their own interpretations. So let me address the question directly. Why does the blue glow of this comet surprise astronomers? Comets can appear blue when carbon-based molecules, particularly diatomic carbon and cyanogen, fluoresce under ultraviolet sunlight. This is well documented. What makes 3I Atlas noteworthy is the intensity and consistency of that blue emission, which correlates with the high carbon dioxide content we discussed earlier. It is unusual, but unusual is not the same as impossible or artificial. Why is the path so precisely calculated? Because we have centuries of experience in celestial mechanics, and because multiple observatories around the world have been tracking this object for months, refining the orbital parameters with each new data point. Precision in trajectory calculation is not evidence of artificial guidance. It is evidence of good science. But again, in an environment where every detail is being scrutinized, these explanations sometimes feel insufficient to those looking for something more. At this point, I want to pause and ask you a question. Based on everything we have discussed so far, what do you think is the most likely explanation for the anomalies surrounding 3I Atlas? Is this simply an unusual but entirely natural comet from a very different stellar environment, behaving in ways we have not seen before because we have so little data on interstellar objects? Or do the accumulating oddities, the nickel enrichment, the symmetrical jets, the low-velocity antitail, the non-gravitational acceleration, point to something we do not yet understand about cometary physics? Drop your thoughts in the comments. I am genuinely curious to hear how you are interpreting this data, because the scientific community itself is divided, and crowdsourcing perspectives sometimes reveals angles that individual researchers miss. Now let's look at what comes next, because the observation campaign is far from over. The European Space Agency's JWST mission, which is en route to Jupiter and its moons, turned its instruments toward 3I Atlas between November 2nd and November the 25th. JWST is equipped with high-resolution cameras and spectrometers designed to study icy bodies, making it an ideal platform for detailed cometary analysis. The raw data has been collected, but the full analysis will not be released until sometime in 2026, after the science teams have had time to process and verify their findings. That is standard procedure, but it means we are in a waiting period, watching the comet recede while knowing that critical data exists but is not yet public. Simultaneously, and this is a detail that has received less attention but is equally significant, the United Nations Office for Outer Space Affairs is conducting an international exercise on comet tracking and planetary defense, running from November 27th through January 27th, 2026. This exercise uses 3I Atlas as a test case, simulating how the global community would coordinate observations and potentially respond if an incoming object posed a threat. To be clear, 3I Atlas itself poses no threat. Its trajectory is well understood, and it will not come anywhere near Earth. But the exercise is designed to test communication protocols, data sharing frameworks, and decision-making processes. The fact that an interstellar object is being used for this exercise is not coincidental. Interstellar objects arrive with less warning than solar system comets, because we cannot predict them years in advance. They are already on approach by the time we detect them. Understanding how to rapidly characterize and track such an object is a legitimate planetary defense priority. But inevitably, when you combine a mysterious comet with a UN planetary defense exercise, it feeds the narrative that authorities know more than they are publicly disclosing. Let's step back and look at the broader context, because 3I Atlas is not occurring in a vacuum. It is the third confirmed interstellar object we have detected. The first, Oumuamua, in 2017, was unlike anything we had seen before. No detectable coma, extreme elongation, and anomalous acceleration that was eventually attributed to outgassing too faint to observe directly. The second, 2I Borisov, in 2019, looked and behaved like a fairly typical comet, albeit one from another star system. Now we have 3I Atlas, which shares characteristics with both. It has a visible coma and tail like Borisov, confirming it is actively outgassing, but it also has compositional and dynamical oddities that echo the mysteries of Oumuamua. What does this tell us about the population of interstellar objects? Statistical models suggest that thousands of such objects pass through the inner solar system every year, but most are too small or too faint to detect. The three we have found represent the tip of an enormous iceberg. As our survey telescopes improve, particularly with projects like the Vera Rubin Observatory coming online, we will detect interstellar visitors far more frequently, potentially several per year. Each one will be a snapshot of a different stellar environment, a different epoch of galactic history. Some will be water-rich, some carbon-rich, some metal-rich. Some will have irregular shapes, some will be more spherical, some will outgas violently, some will be inert. The diversity we are already seeing with just 3 objects suggests that interstellar space is filled with a bewildering variety of debris, the shattered remnants of billions of years of planetary formation, collisions, and stellar evolution. But here is the uncomfortable question that Loeb and others keep pushing into the conversation. If interstellar space is filled with debris, and if intelligent civilizations exist elsewhere in the galaxy, is it not statistically plausible that at least some of that debris is artificial? Not necessarily probes designed to study us specifically, but perhaps defunct spacecraft, discarded components, or even deliberate survey instruments sent out millions of years ago by civilizations long gone. The galaxy is 10 billion years old. Our industrial civilization is barely 2 centuries old. If technological species arise even rarely, the accumulated artifacts from millions of years of activity could, in principle, be drifting through the galaxy, and we might occasionally intersect one. This is not a fringe idea in terms of physics or statistics. The question is entirely about probability. How common is intelligent life? How long do technological civilizations last? Do they build interstellar probes? And if so, how many? We do not have answers to any of these questions, which means we cannot definitively rule out the possibility, but we also have no positive evidence to support it. We are left in the frustrating position of saying it is possible, but unlikely, and that ambiguity is fertile ground for both legitimate scientific inquiry and unfounded speculation. So let's return to the hard data and ask, what would it take to definitively determine whether 3I Atlas is natural or artificial? First, we would need resolved imaging of the nucleus itself, clear enough to see its shape, surface texture, and any structures that might indicate non-natural geometry. None of our current instruments can achieve that level of detail at the distances involved. Second, we would need continuous monitoring of the outgassing to see if the jets vary in ways inconsistent with solar heating alone. If the jets activate or deactivate in patterns that do not correlate with sunlight exposure or rotation, that would be a red flag. Third, we would need to detect any radio or optical signals that could not be explained by natural emission mechanisms. Hydroxyl masers, as mentioned earlier, are natural, but a narrowband signal at a non-molecular frequency would be highly suspicious. Fourth, we would need to measure the trajectory with extreme precision over an extended period to see if there are course corrections beyond what outgassing can explain. If the non-gravitational acceleration changes in magnitude or direction without corresponding changes in observed activity, that would warrant serious investigation. None of these smoking guns have been found. Every anomaly observed so far has at least one plausible natural explanation, even if that explanation requires us to stretch our models slightly or invoke conditions we have not encountered before. The reality is that we are still in the early stages of interstellar object characterization. We have only been systematically searching for these visitors for a few years, and our observational tools, while impressive, were not designed with this specific task in mind. The next generation of telescopes, both ground-based and space-based, will give us far better data. The Vera Rubin Observatory, with its massive field of view and rapid cadence, will detect fainter and more distant objects. The James Webb Space Telescope, with its infrared sensitivity, can probe the composition of cometary ices and dust in unprecedented detail. Future missions, potentially including dedicated flyby spacecraft that can be launched on short notice to intercept an interstellar visitor, could give us close-up imagery and in-situ measurements. That is the future we are building toward. In the meantime, we work with what we have, and what we have is a comet that defies easy categorization. Let's talk about the implications. If 3I Atlas is indeed a natural comet, and I want to emphasize that this remains the most likely explanation given current evidence, then it is teaching us that comets from other star systems can have wildly different compositions and behaviors than what we see in our own solar system. That has profound implications for planetary science. It means that the conditions under which planets form, the chemical makeup of protoplanetary disks, the dynamics of planetary migration and ejection can vary far more than our models currently predict. Every interstellar object is a data point in a vast parameter space we are only beginning to explore. The nickel enrichment alone suggests that 3I Atlas formed in a region of the galaxy with a different star formation history than our Sun's birthplace, possibly an area where more massive stars had already gone supernova, seeding the interstellar medium with heavy elements. Studying these objects is, in a very real sense, galactic archaeology. We are learning about the history and structure of the Milky Way by examining the frozen relics that drift between the stars. If, on the other hand, and this is purely hypothetical, 3I Atlas were found to have characteristics that could not be explained by natural processes, the implications would be staggering. It would mean we are not alone, not just in the abstract sense that life exists somewhere out there, but in the immediate sense that evidence of that life has entered our solar system. It would mean that our corner of the galaxy is under observation, or at least has been in the past, by entities with technology advanced enough to send objects across interstellar distances. It would raise questions about intent, about whether such objects are passive observers or active participants in some larger project we cannot yet comprehend. It would force us to reconsider our place in the cosmic order and accelerate efforts to develop our own interstellar exploration capabilities. But we are nowhere near that conclusion. We are not even close. What we have is a set of observations that are interesting, puzzling, and in some cases difficult to explain within the narrow band of cometary behavior we have previously documented. That is not the same as evidence of artificiality. It is evidence that the universe is more complex and surprising than our limited experience has prepared us for. This is the crucial detail. The burden of proof for an extraordinary claim is extraordinarily high, and rightly so. Science operates on the principle that extraordinary claims require extraordinary evidence, a standard articulated by Carl Sagan and upheld by the scientific community ever since. The evidence for 3I Atlas being artificial is not extraordinary. It is not even particularly strong. It is suggestive only if you are predisposed to see patterns and intentionality where none may exist. But the evidence that 3I Atlas is unusual, that it does not fit neatly into our existing taxonomy of comets, that is solid. And it is that unusualness that drives the scientific process forward. We do not learn by confirming what we already know. We learn by encountering things that do not fit, that challenge our models, that force us to refine our understanding. So where does this leave us as 3I Atlas continues its journey out of the solar system, destined never to return? We are left with more questions than answers, which is both frustrating and exhilarating. We are left waiting for the full spectroscopic results from JWST and Hubble, for the processed data from JWST, for the outcomes of the UN tracking exercise, and for whatever additional observations can be squeezed out of our telescopes before the comet fades from view. We are left debating the nature of scientific skepticism, the role of speculation in advancing knowledge, and the balance between open-minded inquiry and rigorous evidence standards. We are left wondering whether the next interstellar visitor will clarify the picture or deepen the mystery. And we are left with the humbling reminder that even in an age of billion-dollar space, telescopes and planetary science missions, even with all our technological sophistication, the universe still has the capacity to surprise us, to present us with phenomena we did not predict and cannot immediately explain. If this deep dive into the data and the debates surrounding 3I Atlas has given you a new appreciation for just how complex and uncertain the process of scientific discovery can be, do me a favor and hit the like button. It genuinely helps the algorithm push this kind of detailed science content to more people. And in an information landscape dominated by sound bites and sensationalism, we need more spaces for nuanced, evidence-based analysis. The story of 3I Atlas is far from over. As December rolls in and we approach the closest approach to Earth, more amateur and professional observations will flood in. As the official analyses are released in the coming months, we will get clearer pictures, better spectra, more refined trajectory data. And if history is any guide, those answers will spawn new questions, because that is how science works. It is an iterative process, a conversation between observation and theory, between what we see and what we think we understand. For now, we watch and we wait. Telescopes trained on a tiny point of light receding into the darkness. a visitor from the depths of space carrying secrets about the galaxy's past and perhaps, just perhaps, hints about its present. The mystery of 3I Atlas is not whether it is a probe from an alien civilization. The real mystery is what it tells us about the diversity of matter in the universe, the processes that shape objects in the frigid expanse between the stars, and the limits of our current understanding. Those are the questions that will keep astronomers working through the night, poring over data, refining models, and arguing passionately about interpretations. And those are the questions that should keep all of us curious, because the answers, when they come, will reshape how we see not just this one comet, but the entire cosmic environment we inhabit. This is the frontier of knowledge, the edge where certainty gives way to possibility, and it is a privilege to witness it unfold in real time.